Prokaryotes have self-splicing introns. Eukaryotes also have introns, but we don't have self-splicing introns. For us to remove our introns, right, when we're removing our introns, when we're splicing them out, we need a spliceosome complex, which is made up of what? SNRPs, SNRPs, right?
Okay,
SNRP, SNRPs. So it's made up of ribozyme, right? Ribozyme, and it's also made up of what? Ribozyme and proteins, right? And so then my question to you now is, what is cDNA? So can we incorporate, before that, can we incorporate a eukaryotic gene? Can I incorporate this eukaryotic gene with its exons and introns into a prokaryote and have it be expressed? Yes or no? If I were to cut out a eukaryotic gene, right? Say we have an insulin gene inside of us. If I cut it out and put it exactly the way it is, if I placed it into a prokaryote, would it be functional?
no, because
Because
it's
what?
not going to have that spliceosome to take the introns.
Exactly, because the introns are not non-protein coding for the gene, right? They do have a role in eukaryotes for gene regulation, but it's not something that's required. It's not coding for amino acids for that protein that's making, right? So if you incorporate a genomic DNA, right, genomic piece of DNA, a DNA from eukaryotes that has introns and exons in it, it will not be able to be expressed inside of a prokaryote. So in order to do that, in order to express a eukaryotic gene inside of bacteria, since bacteria don't have spliceosomes, we have to remove the introns for them. And so now my question to you is, what is cDNA?
So
It's a type of DNA, right? It's a type of DNA, but what kind of DNA is it? Why is it called cDNA? What does the C stand for? Complementary DNA, right? So you remember some of it, right? You were able to tell me what it stands for. Well, what is it though? So a hint, it's made from mRNA. It's made from mature mRNA. So mature mRNA means it's an mRNA that has been transcribed from DNA, right? It's been transcribed from DNA, and now you have it has the cap on it. It has the introns removed, and it has a tail on it. So you're using mature mRNA to make complementary DNA. So what enzyme is required to make mRNA into DNA? Spliceosomes is to remove introns. What enzyme is needed to make mRNA or RNA into DNA? Remember that central dogma of DNA?
It's a DNA polymerase.
Yeah, DNA. Arrow. RNA. Protein. So this was like the central dogma, right?
Yeah.
But now we know that this is bullshit, right? Why is it bullshit? Because the idea of the central dogma was DNA turns into RNA, RNA turns into protein, and it only goes in one way. It's one-way traffic. There's no going back. But we know this is wrong. And because there's this, we can do this. We're able to turn, right? We're able to turn this guy right here, right, into DNA. Let me do a better arrow. We're actually able to do this, RNA into DNA. So there's a special molecule required for that, a special enzyme. What is it? So what can you tell me about retroviruses, retrotransposons? Why are they called retro?
They can reverse.
Reverse what? There's another word now. You got the first part right of that enzyme's name. Reverse what? Just for the T.
Transcriptase?
Exactly. Reverse transcriptase. So the enzyme, right? Enzyme. reverse transcriptase. So the reverse transcriptase is the enzyme that can help us turn RNA into DNA, right? And this is a enzyme that's in our telomeres, right? That's how telomeres function. Telomerase. It's our reverse transcriptase. We have retroviruses that are also doing this. So, the HIV virus, for example, is a retrovirus. It has RNA that it inserts into our cells, and then it uses reverse transcriptase to turn that RNA that it injected into DNA, and then that DNA is incorporated into our genome, right? And then a similar function is with retrotransposons that also have reverse transcriptase to basically cut themselves, cut and paste, or copy paste. Okay, now tell me, how are you making complementary DNA?
Reverse
So
transcriptase.
remember, that's key to it, right? We take mRNA, so mature mRNA. Mature mRNA, does it have introns?
Not at this time.
Does mature mRNA have
Yeah.
introns?
No.
We remove them, right?
Yeah.
Plus reverse. So if you have mature mRNA, right, and then you reverse transcribe it, you end up with double-stranded DNA or single-stranded DNA? So you have an mRNA transcript. Let me draw for you guys. Let's say this is a piece of mRNA, right? 5' mRNA, right? You got, let's say this is 2AG, blah, 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 blah. Then you have 2AA, right? So now this is going to be the mRNA. This is single-stranded, right? mRNA is single-stranded, right? So now if I add reverse transcriptase, I'm going to end up using complementation, right? Make a complementary side. So now I end up with DNA here, right? 5'. DNA. But is this DNA single-stranded now or double-stranded?
Single?
Single-stranded, right? Obviously single-stranded. And so now to make it double-stranded, right? To make this double-stranded, what you're going to do is you're going to separate these two, right? When you separate them, then you're going to add on DNA polymerase, right? You're going to add a primer and then DNA polymerase, and that's going to basically result in, so this is going to be, first you have single-stranded DNA, right? Single-stranded cDNA. So then you want to make it double-stranded, and so you add DNA polymerase. Then you want to add a primer. I don't know if you guys can see that. So it's saying mature mRNA. Can I do this? All right. So yeah, mature mRNA plus reverse transcriptase gives us single-stranded cDNA, right? It's going to be single-stranded because you're just using this as a template. And then to make it double-stranded, because we want to make DNA double-stranded, we add DNA polymerase plus a primer, and that gives us double-stranded DNA, cDNA. And then this is what we can take, right? We can take this and then incorporate into a prokaryote of bacteria. And that will allow us to have a functional gene product. So remember, the idea of the central dogma was that DNA goes into RNA, which goes into protein, and it was thought of as a one-way street. But now we know that thanks to this enzyme reverse transcriptase, you can have RNA go into DNA. So this is wrong, right? The idea of this is wrong. And so now, going back to that question I asked you guys, what can be a consequence of bacteria having, or not even bacteria, let's see, yes, how's it going, Lee? So we have spreadsheet, so you gotta have essays on the final, right? You didn't know that? Did you know that or no?
Essay?
Yeah, you're gonna have 3 out of 5 essays you have to pick. So out of 5 essays, you have to pick 3 for your final.
Question number one?
No, it's not.
So I was telling the guys here that
Wait, this isn't the
No, it's not doing that.
for the final exam, you guys need to know the role of introns in terms of gene regulation. Okay? So introns aren't junk DNA, right? It's a misnomer because we have they have a role in RNA interference, and they can basically you have siRNA and microRNA, and microRNA can go ahead and silence your own mRNA transcript by binding to the 3' UTR. And that's a form of gene regulation in eukaryotes, right? Because prokaryotes don't have introns. Well, they don't have introns the way eukaryotes do. Prokaryotes do have self-splicing introns, but they don't use introns for gene regulation as eukaryotes do. Okay, at least to what we know right now in research.
The 3' UTR, does that start at the stop codon?
He starts right after, yeah,
Okay.
right after the stop.